We work within an extension of Poincaré gauge theory of gravity, situating its geometric structure within a non-homogeneous timescape cosmological setting on a non-flat distributional spatial background. A 3+1 decomposition is adopted, in which spatial geometry is taken as ontologically primary. Time enters the framework solely as an ordering parameter indexing successive configurations of the spatial geometry and carries no independent state. The Poincaré group is inherently a space-time symmetry group, and the 3+1 decomposition implicitly restricts its operational realization to spatial sectors. This is consistent with standard canonical formulations and is understood as such here. Under local gauging of the Poincaré group, two irreducible geometric field strengths arise: curvature from the Lorentz sector and torsion from the translational sector. These are not introduced ad hoc, but follow directly from the gauge structure. We adopt a non-minimal Einstein-Cartan formulation in which torsion is dynamical and propagating, and is treated as co-primary with curvature rather than algebraically constrained by local spin density. The background geometry is taken to be distributional, motivated by the timescape setting in which inhomogeneity is physically fundamental rather than a perturbation of a homogeneous manifold. Standard FLRW reductions are therefore not assumed, and geometric structure is permitted to vary across domains without enforcing global homogeneity. Given that time carries no independent state, all persistence, propagation, and continuity must be realized within the spatial geometric fields and their associated connection structure governing transport and persistence. No admissible mechanism exists within the framework for storing or transmitting physical quantities through a temporal carrier. Any quantity that exhibits persistence or transport must therefore be carried in geometric degrees of freedom on the spatial manifold, with such transport governed by the connection and persistence consisting in structure carried across successive spatial configurations. Within this constraint, angular momentum cannot be treated solely as a property localized to matter fields or mediated entirely through electromagnetic interactions, as such accounts do not provide a geometric mechanism for persistence once the temporal carrier is removed. In Poincaré gauge theory, intrinsic spin couples directly to the torsional degree of freedom, while curvature couples to energy momentum. In a non-minimal Einstein-Cartan setting where torsion is dynamical, the torsional sector constitutes the only geometric degree of freedom capable of carrying and transporting spin-related structure independently of matter localization, specifically in relation to the distribution and persistence of the spin-sourced component not captured by local matter field decompositions. It follows that, within this framework, the distribution of angular momentum must be realized in part through the torsional sector of the connection. This is not introduced as a proposal, but arises as a necessary consequence of the combined constraints. Time carries no state, persistence must be geometric, and torsion is the geometric field strength sourced by spin. The problem is therefore not whether torsion can act as a carrier, but whether the torsional sector admits stable, propagating configurations that carry angular momentum and remain well-defined under the evolution of the spatial geometry, with such configurations constituting a candidate geometric locus for contributions not otherwise accounted for within standard decompositions. The framework thus reduces the question to a concrete requirement: to determine the existence, stability, and transport properties of torsion configurations sourced by spin on a distributional spatial background, and to assess their contribution to the large-scale distribution of angular momentum in an inhomogeneous cosmological setting. Within the present framework, spatial geometry and its associated connection structure constitute the only admissible carriers of persistence and propagation, with time treated solely as an ordering parameter indexing successive spatial configurations and excluded as a state-bearing entity. Accordingly, no persistence or transport can be attributed to temporal succession itself, and any quantity that exhibits persistence or transport must be carried in geometric degrees of freedom on the spatial manifold, which are exhausted by curvature and torsion arising from the gauged Poincaré structure, with no additional independent geometric carriers admitted. Transport is governed by the connection, and persistence consists in structure carried across successive spatial configurations, admitting invariant geometric residue under closed transport, holonomy. In the present context, this applies specifically to the distributed, spin-sourced component of angular momentum realized through the torsional sector. Within this constraint, angular momentum cannot be treated solely as a property localized to matter fields or mediated entirely through electromagnetic interactions, as neither provides a geometric mechanism for persistence once time is excluded as a state-bearing carrier, and therefore cannot account for sustained distribution without recourse to a geometric carrier, and therefore require geometric representation to remain well-defined under successive spatial configurations, insofar as the distributed non-local component of angular momentum, not reducible to local matter field contributions, is concerned. It follows that the torsional sector of the connection, as the geometric field strength sourced by spin, is the only admissible degree of freedom available to carry and transport angular momentum, given that persistence must be geometric and time carries no independent state, and that curvature, as the geometric field strength associated with energy momentum, does not couple directly to intrinsic spin as an independent source in the same manner, and is therefore not positioned to account for the distributed, spin-sourced component under this constraint. A structurally analogous hierarchy appears in the hadronic sector of quantum chromodynamics. Compact multiquark states, including hexaquarks, correspond to configurations in which all constituent degrees of freedom are confined within a single bound object. By contrast, molecular hexaquarks, defined as dibaryon systems in which two baryons remain intact and are weakly bound by residual strong interactions, represent a higher-level organization in which substructure persists. While candidates for molecular tetraquarks and pentaquarks have been observed experimentally, molecular hexaquarks remain in a predictive regime, with concrete, testable expectations, but no confirmed observations. The relevance of this hierarchy is structural. It demonstrates that physical systems need not collapse all degrees of freedom into a single compact configuration, but can instead sustain layered organization in which lower-level structures persist and participate in higher-level binding governed by distinct interaction regimes. This provides a constrained admissibility bridge for the present framework. Under this mapping, matter-localized spin corresponds to the lower-level source structure, while the torsional field provides a candidate, higher-level geometric configuration space. The speculative extension is that, subject to the constraint that persistence must be geometric, angular momentum may be realized not only as a local property of matter, but also as extended configurations within the torsional sector. These configurations would not be reducible to point local responses at spin density, but would instead constitute distributed geometric structures sustained by the dynamics of the connection, with their persistence realized through structure carried under connection-defined transport, analogous in structural organization to regimes in which persistence extends across scales without collapse into a single localized configuration. The analogy is aligned in status. Just as molecular hexaquarks are theoretically predicted but not yet empirically confirmed, the existence of extended torsion-mediated angular momentum configurations is not asserted but posed as a concrete, testable possibility. The hadronic example serves only to demonstrate that such higher-level organization is admissible within physical theory, not to provide evidence for its realization in the geometric sector. Geometric contribution to angular momentum and implications for the proton spin crisis. This opens the possibility that part of the angular momentum budget attributed to unresolved or distributed contributions in hadronic systems is not contained within matter fields alone, but is instead realized geometrically, with its distribution and persistence carried through the torsional sector under connection-defined transport, and therefore absent from standard decompositions. In this view, the total angular momentum of a system may be decomposed into contributions from quark spin, gluon spin, orbital angular momentum, and a geometric component associated with the torsional sector, with the latter not reducible to localized matter field degrees of freedom. If angular momentum cannot be treated solely as a property localized to matter fields or mediated entirely through electromagnetic interactions, then part of the angular momentum budget may instead be realized geometrically, raising the possibility that the apparent deficit identified in the proton spin crisis reflects an omission in the decomposition framework rather than an unresolved redistribution within the matter sector, with the torsional sector providing a candidate geometric channel for this contribution.